So the query evaluation was one of the main jobs of the DBMS, right? So we know that SQL language is a declarative programming language. Okay, what does it mean? It means that we are not. It means that we are not explaining, and we are not. When I'm not recording on my computer because my computer doesn't record, so just record. Okay. And we don't have anything to write. So, and I made the slides bigger to. So now, in order to process a query, we know that computer systems are using imperative languages. In order to use SQL as a declarative programming language, we have to transform and translate these programs into declarative or imperative programs. It means that we have to transform and translate these statements and these expressions to some statement that are implying the steps we have to take in order to get the result back. So how can we translate these expressions? Not expressions, but these programs, these SQL programs, queries. We knew that every SQL program has an equivalent expression in this process algebra, right? And process algebra expressions, we can interpret process algebra expression as imperative language. Why? Because we can give a plan to process a relation algebra expression, right? So in order to evaluate the query, what we are doing is basically what we are translating, or we are giving a translation of SQL programs to process algebra, relational algebra, and then execute the query based on query execution plan we are creating out of the relational algebra expressions. So, okay, so this is one example of how we can translate SQL queries to relational algebra expressions. From now on, if I tell you process algebra, you just translate it in your brain to relational algebra. I don't know why I mistakenly saying process algebra. Process algebra is another topic in computer science. So suppose that you have this query, select distinct target list from R1 to Rn when condition is held. So we know that in order to compute this, what we are supposed to do is we have to compute the Cartesian join of relation R1 to Rn, and then finally check the condition. If the condition is held in and satisfied by any row, then we have to select that row, and then finally we have to project the columns that are desired here. For example, the target list. Oh, you cannot see the most part. Okay, the target list over there shows which columns are required and expected, and then we are projecting those columns. So so this is very inefficient query. Why? Computation of Cartesian join or Cartesian product of two relationship is very costly. Why?
Because it just multiplies the number of tuples.
Yeah, multiplies, and no matter if any value is equal or not, it should output the whole Cartesian product, which is inefficient. Okay. So suppose that we have these two tables, professor and teaching. So the professor is this query is related to what you saw a few minutes ago in your quiz. Suppose that you have a table of professor and teaching, and the table of professor is not very big. But the table of teaching is big because it's a time-stamped record. What does it mean? Time-stamped record? A record increased by the time. You know, for example, for the teaching table, each semester you are adding a lot of records. without removing any records. These kinds of tables are growing, right? These kinds of tables are containing rows time-stamped. Okay, each row has a time and the rows are increased, the number of the rows are increased. So you can see lots of these examples in financial markets, right? Or in human resources. When you are paying for everyone, you are paying to employees, and every month you are adding records. So these type of records, these type of tables are getting bigger, but you know that this one is small. So if we want to compute the Cartesian product of these two tables, it will be very inefficient. Why? Because if we know the professor ID, then we can filter a lot of records before computing the Cartesian product. Okay? Suppose that the professor table has 100 professors. Okay? And you are interested just in one professor. If you do not filter the Cartesian product before selecting that professor, then you have to multiply the output of teaching to 100. But otherwise, you have to just check some values in the teaching table. So this is a difference between these two execution plans. So the result of this query could be very small. The result could be less than 100. But computing the intermediate table of professor multiplied to professor times to teaching could be more than 500 megabytes. So what is the problem? We are looking for an efficient translation of each query. So the query we saw here a few minutes ago can have very costly translations. Can be translated to a very efficient and optimized manner. Okay, so let's see. We saw this diagram before. Suppose that we have a DBMS, and in the DBMS keeps a system catalog. Okay. What is a system catalog? What is the system catalog?
Like a printer.
What?
Printer for the database.
Not front-end, no. The system catalog is a list of tables, or the tables keeping the name and the name of the tables, the attribute of the tables, the scheme of the database. The system catalog is an internal representation of your database. We read about this, right? We discussed about this when we were discussing about the schemas and so on, right? Didn't we discuss about this? Anyway, system catalogs are a bunch of information about the tables you have, the views you have in the database, and what kind of attributes each table has, and so on. So for your project, okay, when you are writing a report, at the end of the report, you can use system catalog to create queries and write queries about your system and show what kind of tables you have in terms of queries. Okay? So we have the DBMS. The DBMS uses system catalog to check what kind of tables the system has. Then you give a query to the system. Then there is a SQL parser, get and checks the name of the tables and symbols you have in the DBMS. Parse the query. Then you will find an equivalent relational algebra expression for that query. Okay. So a relational algebra expression is found. Now what is the task? This is the topic of this chapter, query optimization. Now we have to either translate the relational algebra expression to a more efficient expression using two factors. One is query plan generator, the other one is cost estimation. Why? Why? The row ladies with why? Because we need to know the cost of execution of each relational algebra expression, and in order to know the cost of the execution, you need to generate or assume some execution plan for each of those expressions. Then what you're supposed to do is you have to compare the cost. The best one is chosen. So in order to know the cost, what kind of information you need?
Size of tables.
Size of the tables, the quiz you gave a few minutes ago. The size of the tables, hold on, how many people chose hash join in the quiz? How many people chose merge sort? How many people, what was the other answers?
Block nested and
Block
index
nested.
Block nested join index.
Index.
What and sort and the, what was it and
Query was not correct.
yeah.
Options, Professor.
No, it was you were supposed to choose the best one, right? Okay. How many chose? How many people chose? What was it? Nested.
Block nested join and index nested join.
Index nested. How many people use nested index join? Okay. I want to give the quiz this answer any people. Okay, I'll change it. The answer is block nested loop joins. Why?
Why? That's why we
Why? Listen, the department table is very small.
That we
It can be, you discuss in the quiz, you know, you didn't discuss, okay. The block table can fit in it's a few number of rows, right? It can be loaded without any cost. And the rest will be scanning the table, the other table. So,
We didn't see the
but
table,
I told you
that's why
that
it's
the
not
question has a trick and is a very tricky question.
I checked the
So,
table.
sorry about that, but
Check
you guys, you have
the
to have
Check the
some
index
estimation
and
about
all.
the number of the records in each table, right? This is the point. Don't worry about that, it's just 2 points, you know, the quiz is not very...
Like the 2
Every
points,
day
3
two.
points, everything we're losing.
And then after we choose the optimized query execution plan, then we have query processing, we have query plan interpreter, which interprets the given optimized relational algebra expression and execution plan, and then process the query based on what we learned in the previous chapter. So basically, query optimizer is using a few number of heuristics to
Why it will not be indexed?
what? Okay, so let me explain. Okay, I told you the answer. So I cannot use the quiz again because when you are using hashing the hash join, right? You are doing 2 steps. One is hashing and checking who is pointing to which bucket, okay, and the other one is selecting the records, okay. So when you can just go with one scan. So because for hashing also you need to scan. You need to scan, do the hashing, check the buckets, right? But while you can, in order to create the join, you can just do one scan with nested loop join, isn't it?
Why can't it be indexed loop?
What?
Indexed loop join. Why can't it be?
Because again, you're adding something that is not required. You're doing indexing when index doesn't have any help. You have to, for any kind of indexing, you have to take additional steps to find records. What is? I'm not. We are. What are you doing in the hash index? Index join. You have one relation like R and A. You have this, right? You are retrieving one record from this, going to the index and checking the other record from this one. Okay? Suppose that this is, what was the table? History department, employee department history. A lot of records. The best index could be, for example, hash join, hash index, or B+3. For all of those indexes, you have to take additional steps. Okay? So why don't you just, for each of these rows, put outside the value of the department, value of the person. You know, this is using nested loop join. It's just one scan of employee history, not using any index on any. But when you are using index join for each record of the employee history, you are going to the index and retrieving the person. Is it good? No.
If it is clustered, actually, you can directly go to the indexes and you can get it easily.
Clustered, again, if it is clustered, clustered on what? Is it possible that this become a cluster? No. Why?
It's an idea only.
No. Because here, what is the field? What is the attribute?
Department ID.
Okay, what is the attribute, right? So, this is in department employee history. How many values does it have? For example, how many departments do we have? Let's say 12. You want to cluster, you want to sort this relationship on 12 just values. And also, is department ID a key here? No, it couldn't be, because the key of this relationship is business entity ID.
Business entity.
Right? So definitely it cannot be clustered. Okay.
First I gave you the log. Where did you confuse me?
So we thought that we are using some heuristic to transform expressions from one expression to its equivalent. Okay. Also, we are using heuristic to estimate the cost of relational algebra. Okay. Some heuristic tells us, for example, here, what was the heuristic we used in the quiz? What was the heuristic I used to choose the best answer? How many people chose nested loop join? Even not even one person, or yes, you know, some people left chose that. But anyway, size of the department table was a heuristic, right? I told you the answer because of that. So this the heuristic is used to also to estimate the cost of a relational algebra expression. It is also used to transform one relational algebra to another relational algebra, and it's also used to choose access path for evaluating sub-expressions. Okay? Basically, query optimizers are not optimizing queries. Basically, they are choosing the optimized translation. Right? There are several translations. They are choosing the best one. So this is not basically optimizer. What optimizer means is manipulating something and just changing the best one. So now it's time to translate relational algebra expressions from one relational expression to the other one. So we need some rules, right? So what are those rules? First of all, what is the feature of those rules?
Even if it is translated, the output should be the same. It should not be.
So what was the expectation from the database? You always want the database to return the correct answer, right? Consistency. So if we have a rule that translates one relational algebra to something that is not correct, or it's not equivalent, then it's not good for us. So we need those relational, those translations be exactly correct, which is proved mathematically and logically. Those rules are proved to be correct, and also those rules has some heuristics to be applied. So, how many people are familiar with rule-based languages? Rule-based language. Prolog.
No.
How many people you're familiar with Prolog? So, who else? In Prolog, you know that the whole program is written in terms of several rules. Each rule has a head and several terms in the body. Okay? So here, the same thing. We have some rules. In the head, we are saying that which expression should be resulted. In the body, we are giving the heuristics. Which one is correct, which one is not. Rule-based languages are usually used in artificial intelligence, AI, right? And to use the best choices and using this kind of intelligence and to create these kinds of smart decisions. So here are a few number of rules. So the first rule, for example, these rules are intuitive rules. You can find these rules easily, and intuitively correct. So the first rule is breaking the complex selection into simpler ones. What does it mean? What does it mean?
I mean, instead of nested, you can use nested loops to implement conditions separately.
Right. So suppose that you have this student table. The student table is sorted based on the student ID. Okay. You are looking for a student. Bennett, what's your student ID?
1009221.
We want to find his record and okay, let's say range queries. So we want to find students between Bennett and Praveen. What's your answer? What's your student?
105+1.
Between these two people, who has the name starting with B, for example. Okay, the first name. So in order to answer this query, what's the expression? We have a condition. We have a select. Find this one and this one. What is the index on this table, a student table? The student ID. Name is not indexed. Okay. If I want to directly go and find in this selection, what kind of processing is it? We have this index. Suppose that we use B+3 index as a cluster index on the student table. You have, when was the midterm exam? Last week on Thursday, right? And you, after the midterm exam, you push the reset button and everything gone. And it just, so it is a multiple search, multiple key search, right? You have two keys. One is the range between Bennett and Praveen. The other one is start for B. Okay, the first one is, okay, so if I want to immediately go and compute this expression, I cannot get any benefit from the B+3. Why?
The index is not.
Because the B+3 is not indexed on two fields. It's just indexed on the student ID. So, okay, it's not sorted on the name of the people. So then I have to go and scan the whole thing. Is that good? Is that efficient?
No.
You have to go and it's not efficient. Okay, so you translate. This is the equivalent expression. First, you will find people between Bennett and Praveen, and then you will check the first name. Who is matching the first name? right? So the second expression. So this is the first rule. Break the complex selection into simpler ones. So this is one of the useful translations. What is the other rule? Breaking projections. Okay? What does it mean? What does it mean?
Getting the output in stage by stage.
You are looking for a table which has less attribute than the original one. Okay? You are looking for a relation which has less attribute than the original one. Okay? So the size of this table should be always small. No, the number of the records, the number of rows.
Yes, sir.
Always less, because the duplicates will be deleted, right? It is for relational algebra. So oh, we have eraser over here. Oh, Bennett, can those people see here? Is that visible to right? I have another color.
Then light low line.
I forgot my card, my markers in previous class, sorry. Okay, so suppose that we have name and column and the where is that? Okay, so how many rows?
4.
Is this a relationship or just a table? Is this a relationship or just a table? Is this table also a relationship? Can I consider this as a relation? Can I consider this as a relation?
Yes.
Because it doesn't have duplicates. So what is the difference between tables and relations? In the relational algebra, each relation doesn't have any duplicates, and order doesn't matter. So, but in tables, in practice, duplicates are existing, and also. So suppose that you have this relation. If I have the color of this relation are how many rows? How many tuples I will have? 2. Blue and red. Because we are removing duplicates, right? So always these expressions have these type of expressions have less rows than the whole thing. No, sorry. This is equivalent, okay? But always this relationship has less rows than R by itself, right?
Well, it could have the same if you chose instead of projecting.
The worst case. The worst case. Less than or equal, okay? So if we do this projection step by step, it means that we are sometimes, luckily, removing some of the rows.
But yeah, doing projection twice, it doesn't matter. The
Yeah, when it doesn't matter, but it is a rule, you know. No, okay. So this rule doesn't say that always it is more efficient. It rules just say that these are equivalent.
So what is that ATTR hash?
These are this set of attributes. This is a set of attributes. It's, for example, A and B. Okay.
Set of ATTR.
ATTR.
C.
Okay, this is ATTR set of attributes, right? We can also change the place of selection and join. Sorry, selection and projection. If the number of the attributes here always, or if the condition is always a subset of attributes, you can always,
Professor,
change it.
ATTR dash is equal to A and B, right?
Where?
What you are written? ATTR is equal to A, B, C, ATTR is equal to A, B. In the board.
ATTR is a set. It's a set of A, B, C. ATTR prime is A, B.
So then here, if ATTR is a subset of.
Oh, sorry. This is a subset of ATTR prime. I did a mistake. Yeah. ATTR prime is always greater than ATTR. You can. Oh, thank you for correcting me. Okay. So why do we need to put this condition? Suppose that this condition doesn't hold.
Yeah, if the projection is less than what we require,
Right.
even if the condition satisfies, we don't get all the tuples.
Exactly. Because in order to check this condition, you need some attributes from here, right? And if it is not, if the all the attributes here is not in here, then you cannot evaluate this one. And there are three. Okay, let me go very fast. So these are rules for join. Okay, joins are commutative. Okay, so R join S is equivalent to S join R. Okay, and join R also associative. Okay, you can change parentheses. If you have MV join, then this is the number of the possible executions. It's very hard, very big. So that's why when you have a query with a very big join expression, okay, so it will be very hard for DBMS to find the best plan. Many times, if you do not guide the DBMS, then it will just give up and go brute force algorithm. Yeah, query optimizers cannot look for all of the plans always. Also, we talked about this before. We have this rule that Cartesian product of S and R is equal to R and S joined together if the condition relates attributes of R and S together. And this kind of translation always reduces the intermediate relationship between intermediate computations between R and in this query processing. The other part, the other condition, you have two conditions. Okay, you are supposed to compute the Cartesian product. You remember the example I gave you about professor and teaching table. Teaching is a very big table. Professor is very small. Okay, so what you are doing is you are choosing condition first, and you choose one professor. The professor, for example, Professor Mahmoud. You are looking for the courses Professor Mahmoud. You are looking at all of the combinations of Professor Mahmoud and all of the courses. Okay, so if you want to compute this, one way is computing the whole Cartesian product of the two tables, which is how many faculty we have. 12 multiplied with number of the records in the teaching table. Okay, suppose you have 12 faculty in this department. So otherwise, the second part, the right hand side of this expression, how many records do we need in the intermediate expression? Just to the number of the teaching records. But the other one is 12 times 2 teaching records. Okay. One more point is that this is very important because for timestamp queries, like for example, if you are working in a stock market and you have this timestamp records and the table is growing with the time, so many times you can, if you have this query frequently and this table is very big and timestamp, then what you can do is you can compute this type of relationship incremental. It means that if you have computed the result for previous records, you can just multiply it to the suppose this is S is standing for select sigma. Sigma. Okay, begin. Okay. This one. Is it visible to everyone? No. Is it visible to everyone? So what is the price? What is the cost? You can estimate the cost and go. Let's go.
20,000.
But you cannot go before you estimate the cost.
20,000.
Number of days into records per day.
Well, so let's say we could have definitely more than that. You know, you see the range, it's a range query, guys. Today is
Number of days
November
into
3rd,
queries per
right?
day.
November 3rd, suppose that today is, how many days do you have to search? How many days you have to search?
330 about it was a month.
300, yeah, 330. 330 multiply 2,
10,000. ఇందాక అదే చెప్తాను.
is that correct or not?
Calculation into stock price and correlation pattern.
Suppose that you created the database on January 1st, 2002, after 9/11, right? Suppose that create a database after that. How many records do you have? You have a lot of records. 2002, 15, 14 multiplied to 365, right? Right, no. 13 multiplied to,
3 into 10 power 10.
what?
3 into 10 power 10.
How do you,
The Cartesian product of corporation stock price.
right, the Cartesian product of corporation, how many records you have in Cartesian product?
10,000 records.
Multiply 2. How many years you have? 12 years, 13 years. Multiply to 365,
Total records.
okay? Plus 330, right?
Total records.
Multiply 2. 10,000 will be a lot, okay?
13 into 365.
So, how about,
Google the database start with the records are used.
Oh.
Total records in the database.
how about this one?
into,
10,000?
Then it's only 10,000 times.
10,000.
30 times 10,000.
Right? This is not. Is it correct or not? Everyone got the solution? Everyone got
why 13 into 365?
what? Which one you're talking about? Because we have 30 days, which 303 days, 30 days.
Okay,
From the January 1st, 2016 to today. Today is
No, the 13 into 365 figured
here.
previously, yeah.
Because we assume that the database has been created on January 1st, 2012.
Okay.
January 1st, 2012 means
ఆ రోజు నుంచి ఈ రోజు దాకా ఉన్న అన్ని రికార్డ్స్ మల్టిప్లైడ్ బై స్టాక్ ప్రైస్ ఉన్న రికార్డ్స్ ఫస్ట్ చేసినప్పుడు కార్టేజ్ బాక్లు అన్నిటికీ జరుగుతాయి
2012, 16 అంతా ఉంటుంది 4 years రావుతుంది మళ్ళీ
Sorry, 2002. After 9/11, right?
2002.
I don't have it 2001. Okay, so this is the end of class. So we will return to this topic. Guys, it's very important to, from the next week, we'll have quiz, but not 30 minutes on the quiz. Just be on time. We'll have just 10 minutes on the quiz, and then we'll start lectures. Is that okay? How many people like quizzes? Except the one that we had today, and unfortunately the answer was not correct for everyone.
Then that's what happens.
So everyone likes quiz, right?
Nobody likes